Hello everyone, myself Dr. N.C.H. Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to the today's session on Analytic Function, Part 1. In the last session, we have discussed about limit, continuity, differentiability of a function of complex variable. And in today's session, I am going to introduce an important concept, analytic function. Similarly, harmonic function. Here, in this session, I am going to introduce what is an analytic function, what is an entire function, singular point, isolated singular point, and properties of analytic function, and finally harmonic and conjugate harmonic functions. And here there is another interesting topic called Cauchy-Riemann conditions or Cauchy-Riemann equations. These are the conditions to check the analyticity of the given function f of z. So using the Cauchy-Riemann conditions, we can check whether the function is analytic or not. Simply, if these conditions satisfy, then the function is said to be analytic. If CR conditions are not satisfied, simply the function is not analytic. So, the Cauchy-Riemann equations or conditions are also known as CR equations. Now, the analytic function. Let us consider a function of complex variables f of z. Let a function f of z be derivable at every point z in epsilon neighborhood of z0. That means epsilon neighborhood of z0. What does it mean? This f of f dash z exists for all z such that mod z minus z0 is less than epsilon, where epsilon is a positive, a very smallest positive number. Then f of z is said to be analytic at z equal to z0. Simply, the function f of z is derivable at every point z in epsilon neighborhood of z0. Derivable means the derivative must exist. So, if mod z minus z0 less than epsilon, then f of z is said to be analytic at z equal to z0. So, f dash z exists for all such values of z. Simply we can say, if the derivative exists at a point, for example at z equal to z0, f dash z exists, then the function is said to be analytic at z equal to z0. So, an analytic function is also known as regular or holomorphic function. If f of z is analytic at a point z equal to z0, what does it mean? F of z0 exists and also the derivative of f exists at every point z in the neighborhood of z0. So, if you consider the point z0 here in the neighborhood of that z0, at each and every point the function is derivable. Derivable means differentiable. So, this is the definition of analytic function. A function f of z which is derivable at every point of z in epsilon neighborhood of z0 is called an analytic function. Now, for example, at the point z equal to z0, the derivative exists. And now let us consider a domain capital D, and the derivative exists for all points of this domain, points of capital D. In that domain, at each and every point, if the derivative exists, then the function is said to be analytic on the domain D. So, not only at a single point, not only at a neighborhood, in the neighborhood of some z0, the function is derivable at each and every point of a domain capital D. Then, the function is said to be analytic on the domain capital D. And coming to the next definition, entire function. if the function f of z is analytic at each and every point of in the entire complex plane. Let us consider all the complex points. If the function is derivable at each and every point in the entire complex plane, then the function is said to be an entire function. And singular point. Now, for example, let us consider a function f of z equal to z square. Now, what is the derivative of this? F dash z is 2z. So, this derivative exists for all z, particularly in a domain D or in the entire complex plane. Similarly, if I consider a function f of z equal to 1 by z, now what is its derivative? F dash z is minus 1 by z square. Now, for example, at z equal to 1, what is the answer? Derivative is minus 1. Z equal to 2, it is minus 4. So, f dash is minus 1 here. F dash is z equal to 2 minus 1 by 4. Z equal to 3, f dash is minus 1 by 9. Like that, the derivative exists at all the points z equal to 1, 2, 3 and so on, minus 1, minus 2, minus 3 and so on. But at z equal to 0, what will happen? F dash z is 1 by 0 that tends to infinity. That means f dash does not exist at z equal to 0. So, such a point is called a singular point. Simply, a point at which the function ceases to have a derivative, ceases means fails to have a derivative, is called a singular point. Or simply I can say, a point at which the function ceases to be analytic or fails to be analytic is called a singular point. The best example is f of z equal to 1 by z and its derivative is minus 1 by z square, which doesn't exist at z equal to 0. So, in this example, z equal to 0 is a singular point. Similarly, we can define isolated singular point. For example, let us suppose f dash z naught exists at every point in the neighborhood of z naught. If I consider the point z naught and its neighborhood, the derivative exists at each and every point in the neighborhood of z naught, but not at z naught. But f dash z naught does not exist. Then the point z equal to z naught is called isolated singular point. Singular point means simply if the derivative does not exist at a point, that is called a singular point. The derivative exists at each and every point of the neighborhood, but not at that point, particular point, is called isolated singular point. Now, coming to the properties of an analytic function. If f and z, let us consider two functions f of z and g of z. If these two f and g are analytic, then their sum f plus g, difference f minus g or g minus f, whatever may be, the product f into g and f divided by g, where g not equal to 0. The denominator is not equal to 0. If the denominator is 0, that tends to infinity, we cannot define the function. So, g not equal to 0. So, if f and g are analytic, then f plus g, f minus g, f into g, f by g, all these are also analytic. So, f plus or minus g, f into g, f by g, all are analytic. Similarly, an analytic function of an analytic function is analytic. We have an analytic function and the function itself is an analytic. So, analytic function of analytic function is again analytic. Similarly, an entire function of an entire function is entire. These are the properties of analytic function, and not only that, if f is analytic, then f dash is also analytic. If f is analytic, then its derivative is also analytic. Now, another interesting topic is the Cauchy-Riemann conditions or Cauchy-Riemann equations, which are also famously known as CR equations or CR conditions. The necessary and sufficient conditions for the existence of derivative of f of z, where f of z is in the form of u plus iv for all values of z in the domain R, capital R, are given by. So, these are the necessary and sufficient conditions for the existence of derivative of a function f of z, which is in the form of u plus iv, where u is the real part and v is the imaginary part. What are the conditions? These u and v must possess the partial derivatives. All the partial derivatives are continuous functions of x and y. That is the first condition. That means dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. All these are continuous functions of x and y. Here we can use the notation ux, u suffix x for dou u by dou x, u suffix y for dou u by dou y, v suffix x for dou v by dou x, v suffix y for dou v by dou y. So, if these partial derivatives must be continuous functions of x and y, and the main CR conditions are given here. The conditions are dou u by dou x is equal to dou v by dou y and dou u by dou y equal to minus dou v by dou x. So, these are called the Cauchy-Riemann conditions or Cauchy-Riemann equations, simply known as CR conditions or CR equations. So, here we have two functions u and v. Let us find the partial derivatives of these two functions with respect to x and y. Find dou u by dou x, then dou u by dou y, dou v by dou x, then dou v by dou y. Now, the CR conditions are here dou u by dou x must be equal to dou v by dou y. So, dou u by dou x is equal to dou v by dou y. This first and fourth must be the same. And second is dou u by dou y, third is dou v by dou x. So, dou u by dou y, the second one is equal to minus of the third one, minus of dou v by dou x. And these are the conditions for using which we can check the analyticity of the given function. We can check whether the function is analytic or not by checking these Cauchy-Riemann conditions. Here, a function f of z is analytic if u and v satisfy Cauchy-Riemann equations. This is the main point. The given function f of z equal to u plus iv is said to be analytic if the functions u and v satisfy the Cauchy-Riemann conditions. If these conditions are not satisfied, simply we can say the function is not analytic. So, to check whether the given function is analytic or not, first consider the real and imaginary parts, then find its partial derivatives with respect to x and y, and check the CR conditions. If CR conditions are satisfied, then the function is analytic, otherwise it is not analytic. And the next definition is Laplace equation, and this is a well-known equation. Most of you may have known this. The Laplace equation is given by dou square u by dou x square plus dou square u by dou y square equal to 0. That means, if we have a function u equal to u of x comma y, then find the second order partial derivatives of u with respect to x and y, dou square u by dou x square and dou square u by dou y square. Find the second order partial derivatives of u with respect to x and y. The sum of these two must give the answer 0. That is, dou square u by dou x square plus dou square u by dou y square equal to 0. Then u is said to be, then this equation is said to be Laplace equation. And here this is denoted by del square of u is 0. So what is this del square now? From this equation I can write dou square by dou x square plus dou square by dou y square of u equal to 0. I can take this u common. So, and I am giving the notation for this as del square. So del square is dou square by dou x square plus dou square by dou y square, which is an operator called Laplacian operator. Here del square is called Laplacian operator. And the equation, Laplace equation, is simply dou square u equal to 0. Similarly, if we have another function v equal to v of x comma y, then if this v satisfies the equation del square v equal to 0, then this is also called Laplace equation for the function v. And the next definition is harmonic function. The solutions of Laplace equation having continuous second order partial derivatives are called harmonic functions. The solutions of Laplace equation, that means what is Laplace equation? Del square u equal to 0. So the solution of this equation is simply u. So a function which satisfies the Laplace equation is called harmonic function. A function which satisfies the Laplace equation. For example, if dou square u by dou x square plus dou square u by dou y square is 0, then u is simply called a harmonic function. Similarly, if dou square v by dou x square plus dou square v by dou y square is 0, then v is said to be a harmonic function. For example, you consider another function phi. If del square phi is 0, then phi is said to be a harmonic function. So simply the solution of Laplace equation or a function which satisfies the Laplace equation is called a harmonic function. And here there is another important point, that if the function f of z is in the form u plus iv, and if it is analytic, then u and v satisfy Laplace equation. If the function f of z is analytic in the form of u plus iv, then u and v satisfy Laplace equation. Hence, the real and imaginary parts of an analytic function are simply called harmonic functions. The real and imaginary parts of an analytic function are harmonic. And conjugate harmonic functions. Two harmonic functions u and v which are such that u plus iv. So, for example, we have two functions u and v such that f of z is u plus iv. And this f of z is analytic. So, two harmonic functions u and v in the form of u plus iv is analytic. In the form of f of z is u plus iv, which is analytic, are called conjugate harmonic functions. Here u is said to be a conjugate harmonic function of v and vice versa. If f of z equal to u plus iv is analytic and u and v satisfy Laplace equation, then u and v are said to be conjugate harmonic functions. Here f of z is in the form u plus iv, which is an analytic function, and these u and v automatically will satisfy the harmonic function. In that case, u and v are said to be conjugate harmonic function. Now, let us solve some problems on these concepts. Now, the first question, check whether the following functions are analytic or not. So, in that, the first one, solution, f of z equal to z square. Now, we know that z equal to x plus iy. So, therefore, let us substitute that z equal to x plus iy in the given function. So, x plus iy whole square, then simplify it, a square plus b square plus 2ab, and here we know that I square equal to minus 1. Therefore, x square minus y square plus I into 2xy, which is in the form of u plus iv. So, f of z is in the form of u plus iv, where u is x square minus y square and v is 2xy. Now, we need to check whether this function is analytic or not. To check the analyticity of a function, we need to check the CR conditions. So, to check whether f is analytic or not, we have to check the CR equations or conditions are satisfied or conditions are satisfied or not. Now, let us consider u, x square minus y square, and v, 2xy. Let us find the partial derivatives of u and v. So, dou u by dou x is 2x. While differentiating partially with respect to x, we treat the other independent variable as constant. Here we treat y as constant, therefore the derivative of y square is 0 and the derivative of x square is 2x. And dou u by dou y, now with respect to y, we treat x as constant, so here we get 0 and minus 2y. Now coming to this second function, dou v by dou x is now with respect to x, so we can treat y as constant, so 2y is constant and derivative of x is 1 itself, and dou v by dou y is 2x. This is equation number 1, this is 2, 3 and 4. So here we have 4 equations. Now from 1 and 4, it is very clear that from 1 and 4, it is very clear that dou u by dou x is dou v by dou y. And from 2 and 3, you see, second one, dou v by dou y is minus 2y, whereas dou v by dou x is plus 2y. So, how can we write this? Dou u by dou y is minus into 2y means dou v by dou x. So, this is the first condition of CR equation and this is the second condition. So, that implies u and v satisfy CR equations. Therefore, f is analytic. So, like that we check whether the given function is analytic or not. Now, coming to the second problem, f of z equal to xy plus iy, x into y plus I into y. So, which is directly in the form of u plus iv, where u is xy and v is y. Let us find the partial derivatives dou u by dou x, y, dou u by dou y, x, dou v by dou x 0, dou v by dou y 1. Now, again the same, from the above equations, you see dou u by dou x and dou v by dou y, these two must be the same. So, here dou u by dou x is not equal to dou v by dou y. If at least one condition is not satisfied, simply we can say that the function is not analytic. Here both the conditions fail, that is a different thing. Now, dou u by dou y is not equal to minus dou v by dou y. Therefore, u and v doesn't satisfy CR conditions. Hence, f is not analytic. So, like that, by using CR conditions, we can check whether the given function is analytic or not. Similarly, there is another problem, z plus 2z bar. The third one, f of z equal to z plus 2z bar. Yeah, 2z bar. Now, we have z, what is z? X plus iy. That implies, what is z bar? The conjugate of z, by replacing I by minus I, x minus iy is z bar. Now, let us simplify the function first. To check whether the function is analytic or not, we need to check whether the real and imaginary parts of this function satisfy Cauchy-Riemann conditions or not. So, for that reason, first we need to simplify this function f of z in the form of u plus iv, real part plus I into imaginary part. So that's why let us simplify this function first. X plus iy plus 2 into x minus iy. So after simplifying x plus iy plus 2x minus 2iy, and here x plus 2x 3x plus I common, y minus 2y. So which is 3x minus iy. So which is in the form of u plus iv, where u is 3x and v is minus y. Now let us find all the partial derivatives. Dou u by dou x 3, dou u by dou y 0, dou v by dou x 0, dou v by dou y minus 1. Dou u by dou x must be equal to dou v by dou y. But here dou u by dou x is not equal to dou v by dou y. That implies u and v doesn't satisfy CR equations. Hence, given f of z is not analytic. So, if the CR conditions are satisfied, then the function is said to be analytic. Otherwise, simply we can say that the function is not analytic. In today's session, I have introduced a new concept, new and important concept, analytic function, and then harmonic function, and the conditions to check the analyticity, which are CR equations or CR conditions, and also solved some problems on analytic function. So in the next session, we will continue the same. We solve some problems, or we check whether the given function is analytic or not, whether it is harmonic or not, in the next session. Thank you very much.